Welcome back. In previous videos, we discussed the geometry of the subRiemannian Heisenberg group. We got to know the geodesics, and knowing the geodesics, one knows the metric balls. These balls behave differently than in Riemannian geometry. We shall see next some properties of them. In particular, it is interesting to see how the balls change when the radius varies. In rough words, small balls get more and more flat. The geodesics in the subRiemannian Heisenberg group are lift of arc of circles or of lines. So namely, on the xy plane, one has a circle, then one lifts the circles by the method of the area. So the lift is at time t is the region spanned by time t. And now you will see in this picture what happens. You see, when x and y goes around the circle, the z coordinate is increasing. Okay, if you're going in this direction. See, and then the geodesics get higher and higher and higher, stuff like this. Right? So you see this picture. So these are curves that the spirals is not a spiral because you see the height does not grow linearly. The area does not grow linearly in the time of length of this curve. Okay, but this is more or less the behavior. Okay, so this is a picture for a geodesic in the subRiemannian Heisenberg group. Once one has the formulas for the geodesics, considering the geodesic at time 1, one can get to draw pictures of the spheres. Okay, so these are all points. Right? So I'm drawing only half of it, of the sphere. See, so you have straight lines in the final points, and you have other lines that are curves. These are all curves whose projection has length 1. Right? And it's interesting to see that now at the poles you have a curve that projects exactly to a circle, and at this point you will reach again the z-axis. And so these are pictures of the spheres with some geodesics inside. So half of the sphere to see the geodesic inside. And instead, this is a picture of the whole sphere. So if you think it's full, this is the ball. This is the picture of the unit ball. So topologically, we have something that is homomorphic to the ball in R3. Metrically, not really, because you see there is a point here. It's not a cusp. Now in this picture, you see really the section in the xz plane. There is a corner here at the top pole. Okay? So it's a smooth surface except at these poles. Okay, so now this is really what is the exact shape of balls. But now what we would like to discuss is how these balls change when the radius changes, and in particular how the volume change and the rough shape. I will start with a simple and elementary observation on the shape of balls. I will prove this observation very easily without using really any equation on the geodesics. Okay, and I claim this fact: the ball of radius r at the origin of the subRiemannian Heisenberg group. subRiemannian Heisenberg group behaves as a box. Let's see, of the form, let me write, minus r times minus r times minus r square. So you should think of this to be a, so in the xy coordinate, it's really a square. So I'm drawing a square in the xy coordinate. And now in the third coordinate, so I'm thinking that r is small, so it's less than 1. So r squared is is smaller than r. So in the third coordinate, they behave. This length is r squared, which for us less than 1 is less than r. Okay, so I'm claiming that this is the ball. They behave like this, up to inclusion and up to a multiplicative factor. Okay, let me first. Let's prove it, and then we see what I mean with they behave as such. Okay, so indeed. So let's consider the ball of radius 1. Let's B to be the ball, CC ball. Radius. Let's consider a ball of radius R B. Okay. So first, observe that if I take a point x, y, z in the ball of radius R, we have that I claim that both an x and y, these are smaller than r. Since see, when you have a point of x, y, z, right? So if the distance is less than r, it means that there is this admissible curve of length less than r, which means that when I project, since this curve has exactly the same projection, then I connect the point x and the point, the origin and the point xy with a curve less than r, of length less than r. Therefore, so let's say since the length of a horizontal curve is equal to its projection. So actually, really, the vector xy in the plane can be connected with a curve of length r, so its norm is less than r. So in particular, each of the components is less than r. Okay, so x and y are bounded by r. Now, what about z? I claim that also we have a bound on z. Okay, what should be this bound? Okay, so it is the bound of a curve of length at most r. Okay, so now remember that z is the integral from 0 to, so I say the curve has time 1, as parameterized on 0, 1, so I have x dot, x, y dot, minus y, x dot. We can parameterize the curve, so let's do like this. Parameterize, so this is the curve, gamma, parameterize with, let's do it with unit speed. So x dot, y dot, in norm is equal to 1, and therefore the time of the curve is, so gamma is parameterized on 0 r. So here I don't have to put 1, but I have to put r. In dt. Okay, so now let's be brutal and let's estimate, right? So this is r, so x is bounded by r, y dot is bounded by 1. Likewise, y is bounded by r, and y dot is bounded by 1. So I have twice r dt, so which is 2r squared. Okay, so what we understand from this, we understand that the ball, therefore, the ball of radius r is contained in, so the first two coordinates are between r, minus r and r. And the third coordinate is between minus r squared to r squared. Okay, so we have one inclusion. Now let's look at the other inclusion, second. So let's say I want to claim that, so I want to find a box, a box inside the ball of radius r. Okay, so let's say that let's do it first for r equal to 1. Okay, so I claim like this. You see, I'll draw a picture in the xy plane. Now in the xy plane, what I could do, I could, let's say I have length 1 to use. So what I could do, I could move to any point using some length, let's say 1/2, for example. And then what I would like to do now, I would like to gain some area. So maybe before going around the straight line, I will choose to move around a circle. So I will choose a circle, and then move along a line. This way, I will have enclosed some areas, and then I will move along a line. Okay, and I will get to this point with having span area exactly this, right? So say that, for example, I could use half of the length, or less than half of the length for this circle, less than half of the length for this circle. Okay, so therefore, what we have is that, so I claim that if, now we have that x and y okay, let's say we want to use less than half of length. Let's say that, okay, x and y, let's say, are less than 1/10, just to make a number. Okay, so that the norm of xy is strictly less than 1/2. Okay, you can choose what's a better number here, but okay, just 1/10 works. Okay, and if instead z is less than, okay, now what I want to do here, I want to say, okay, what is the area that I can fill with a circle of radius 1? Okay, maybe it's not so efficient to start calculating area of circles, but okay, we can make it even simpler, and we can consider a square. Okay, so now if the square has length 1/10, okay, so the length is still 4 times, so it's still less than 1/2, and the area is 1/100. So if z is less than 1/100, then we can reach the point x, y, z with an admissible curve, lifting the curve that follows a square of side length less than 1/10, and a straight line of length less than, again, 1/10. Okay, so the total length is going to be, total length is 1/10 plus 4 times 1/10, which is less than 1. Therefore, what we proved is that if you take the first coordinate between -10 and 10, and -1/10 and 1/10, likewise for the second one, and then the second one is -1/100 and 1/100, this is contained in the ball of radius 1 at the origin. Okay. Now let's change for general case. Color. For r greater than 0, then what we can take, let's take r/10, so the length is less than r/1/2, and the total length here will be r/10. And now what about the square? So now if we take the square of side length r/10, then the area is going to be r²/10. So this is still the length is r/10. So what we are going to show is that if now take these numbers, then you are inside the square. Okay. In other words, let's write what's called the Ball Box Theorem. The Ball Box Theorem. There exist constants C1, C2. Actually, probably C1 could be equal to 1, such that the box of constant C1r is contained in the ball of radius r, and which is contained in the box of C2r for all r. Let me recall what was the box. Here, box r is -rr times -rr times -r². So this is called the Ball Box Theorem, and we will see some generalization of it. So what we understand really that this ball is not behaving in an Euclidean way when we're scaling. This is scaled linearly, and this direction is quadratically. Let's really see back the picture I show you at the beginning, right? So these are the pictures of the spheres. You see, okay, at unit ball and unit size, this is something that is homomorphic to the ball, the usual topological ball. Now you see, when r grows, then the vertical direction is stretched more, it's quadratically. Right? So these objects are becoming circles here, and then with a cap on top, this is higher and higher with respect to this side. Right? Instead, when r is small, so what happened, because r squared for r small is much smaller than r, the balls are getting much more flat than they're getting smaller in the xy direction. So they're some pancake shape. Okay, still topologically they're balls, but they are flat in the vertical direction. Okay, now what does this tells us about the volume? Okay, so what's clear is that this the volume of this box is this length times this length by this length. Okay, so I notice that the volume of the box radius r is a constant, so probably 8 times r to the fourth, so it's 2r 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 squared. So see, this box behaves as r squared. But we saw in the previous video that we recall that we saw that the volume, not only of the ball of radius at the origin, but really at every other point, this is equal to r for the volume of the ball center at the origin with radius 1. And this was because the left translations were preserving the volume, the Euclidean volume. This is the Euclidean volume, the back three-dimensional measure. Okay, now we'll see next why this property implies that the Hausdorff dimension of the space is not equal to 3, like the Euclidean space, but it's equal to 4. The exact volume growth of metric balls will help us in calculating the metric dimension of the Heisenberg group. So the dimension of the Heisenberg group. Of course, I always mean the subRiemannian Heisenberg group. So topologically, this object is R3. We should have noticed that the distance induces the same topology. But what about the metric dimension? The metric dimension is not going to be 3, actually it's going to be 4. So write it as a proposition. So the Heisenberg group equipped with the standard Carnot-Theodori also called subRiemannian distance has Hausdorff dimension equal to 4. Now, we will recall later in the course what is the Hausdorff dimension defined for general metric spaces. But now I will immediately give you the argument, so one gets used to work with the Hausdorff dimension, even if maybe the theory of behind the Hausdorff dimension is maybe not completely clear. The proof is not difficult. So the proof is going to be enough to show that there exists constant k1, k2, positive constant, such that the minimal number, let's call it an epsilon, of balls, metric balls of radius epsilon needed to cover the unit ball satisfies constants, n1 and n2, k1 and k2 is going to be 1 over epsilon to the fourth. So epsilon to the minus 4, okay? Let's see what this means, okay? So we have the unit ball, and we want to measure the Hausdorff dimension of this object. So what we do, we cover it with epsilon balls, okay? As few as we can, okay? Now, if you are in the Euclidean world, to cover the ball of radius r in the plane, you just need r square balls. If you divide by 1 over n, let's do it like this. If you divide by 1 over n the square, the unit square, you cover it with n square little cubes. So in terms of radius, if you fix the radius to be epsilon, you need 1 over epsilon square balls. Okay, in a three-dimensional Euclidean space, you need 1 over epsilon cube balls. Now instead we will need up to this constant, up to this multiplicative factor, we will need epsilon to the 1 over epsilon to the fourth balls. Okay, so once we have proved this from general theory, we will have that the units the unit ball has Hausdorff dimension 4. Okay, so let's take that this is that this is really equivalent, or actually it's a little bit stronger than having Hausdorff dimension 4. Okay, so if you don't know what is the Hausdorff dimension, for now just take this as the claim that we want to prove. Okay, so let's prove both inequalities. Okay, so let's start with the lower bound. Okay, for lower bound, okay, let b1 be an epsilon, be balls of radius epsilon covering the CC ball of radius 1, then the volume of the unit ball is less or equal, since they cover, the sum of the volume of this balls Bj. Now we know what is the volume, so this is radius epsilon, which means this volume is the constant is epsilon to the fourth volume of the ball, of the unit ball. Okay, so this is equal an epsilon times epsilon to the fourth volume of the ball, unit ball at the origin. Okay, in other words, we have that n epsilon is greater or equal to 1 over epsilon to the fourth. Okay, right, simplify, and you move this on the other side. Okay, now upper bound. For the upper bound, so let b1 bn be a maximal family of disjoint balls of radius epsilon over 2 in the unit ball. Okay, what do I mean? So we have the unit ball, B1. Now I take points, okay, and then what I take it in such a way that the whenever I look at the ball of radius epsilon over 2, then this does not intersect the other balls. Okay, so I take a point and a ball. If it does not cover, I take another point and another ball. If there is room for another ball, I take it until I can stop, right? But by Zorn's lemma, that one such n exists. Okay, so now all these balls are disjoint. Now, one should notice that actually the fact that this is maximal, then if I take now the balls of radius epsilon, then actually they have to cover. But we're not using this, but we are just saying, okay, then the volume of B11, this is less than the volume, the sum of the volumes of the balls, okay, and which are n of them, and all of them have the same volume, which is the radius the fourth times the volume of the ball of radius 1. Okay. Okay, good. And now, as I said, now we're going to say, okay, since Bj is maximal, the balls with same center and radius epsilon make up a cover of the unit ball. Therefore, the smallest possible number of covers is smaller than n, and n from this inequality is less than, okay, is, I have to move this, so 2 to the 4, 16, so 16 divided by epsilon to the 4th. Okay, and this concludes the proof. As a consequence of the fact that the Hausdorff dimension of the subRiemannian Heisenberg group is equal to 4, we get that this geometry is not a Riemannian geometry, not even equivalent up to some Lipschitz equivalence. So let me write it as a corollary. So the subRiemannian Heisenberg group is not locally by Lipschitz equivalent to a Riemannian manifold. Okay, why this is true? Indeed, if it were, the Riemannian manifold would be three-dimensional, would be topologically the same, topologically three-dimensional, like the Hausdorff group, but the Riemannian manifolds are by Lipschitz equivalent to a Euclidean space, and therefore they have, therefore the Hausdorff dimension would be equal to 3 and not 4. Okay? If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below. Bye.